In part 3 of our chapter 18 lecture videos, we're going to cover two of the very important reactions of aldehydes and ketones. These reactions are heteroatom exchange reactions, where the carbonyl C double bond O oxygen is replaced by other heteroatoms. This turns out to be these turn out to be extremely important reactions in biological chemistry, since much of biological chemistry involves heteroatom exchange reactions. We're going to start by uh, looking at a reaction where the carbonyl oxygen is replaced by other oxygens. This forms what are called hydrates and acetals. We have two observed reactions in this section. The first one is a reaction where the carbonyl absorbs water. This proceeds by mixing the carbonyl with water and acid, and it forms a molecule which looks like this, where the carbon atom of the carbonyl is now connected to two OH hydroxyl groups. We call this a hydrate, and this turns out to play a very important role in biological chemistry and also in practical chemistry. Even more important is the reaction where a carbonyl absorbs two molecules of alcohol, so ROH. Again, this requires acid, and we'll discuss what the acids are down below. This forms a product where the central carbonyl carbon is connected to two oxygen carbon groups, OR groups. This is called an acetal. It turns out this particular reaction is a central reaction in carbohydrate chemistry, and we will be revisiting it then in that chapter. Now, when we say acid in these cases, what we are talking about is anhydrous strong acid. By anhydrous, I mean that it's not aqueous. So examples of this that have been used are hydrogen chloride gas, concentrated H2SO4, which has only a minimal amount of water in it, and a new acid that I'm going to introduce to you called PTSA. PTSA looks like this. PTSA stands for Paratoluene sulfonic acid. So here's a toluene. Para to that, we have the sulfonic acid. Sulfonic acid is very interesting because it looks very much like a sulfuric acid, except that one of the hydroxyl groups from the sulfuric acid has been replaced by a carbon group. So it has a very high strength, not quite as high as sulfuric acid, but it's a very strong acid. We like to use it in organic chemistry reactions because it's very soluble in organic substances, unlike sulfuric acid, which is extremely polar, and so when mixed with organic solvents, it forms two layers. We're now going to talk about the mechanism of the acetal formation reaction. And in this context, I'm going to introduce to you some basic concepts of heteroatom exchange reactions that will apply to a number of other mechanisms for the rest of this semester. Now, one of the things about heteroatom exchange reactions, such as acetal formation, is that there are many steps which are all connected together by small equilibrium changes. And in fact, that makes these reactions very large and a little bit hard to remember. So what I've done is I have basically broken these reactions into smaller, what I call phases, because they aren't individual steps, but they're overall changes that occur during the reaction. And then each phase has a very consistently reproduced set of 3 steps, so that if we can understand the phases and then remember the 3 steps, we can string them together and make the overall mechanism. So for example, if we look at the acetal formation, I'm going to scroll back up. Here's the acetal. So what we're going to need to do to make this acetal product from carbonyl and alcohols is we're going to have to add two alkoxy groups. So we're going to have to add this ROH twice, and we're going to have to remove this carbonyl oxygen somehow to make room for the two alkoxy groups. So we're going to break this down then into three phases. The first phase, we're going to add the first alcohol. Then we're going to remove the carbonyl oxygen to make room so that then in the third phase, we can add the second alcohol. Each of these phases will have several steps. They generally occur in the same way. And so what we can do is learn what the three basic steps are and how they occur, and then apply them to the phases. The other thing that is interesting about these heteroatom exchange reactions is that they are generally composed of reversible equilibrium-driven steps. So that we're generally going to be writing these with these two opposing equilibrium arrows. The other thing that you will notice and often will ask is that when we look at a given step, so for example, just if you imagine we have some kind of mechanism like this, we're at a step here, and in our mechanism which goes to our product, we do something which makes a thing here. So for example, maybe we protonate some atom in the molecule. Very often there will be other atoms that could be protonated instead. That would create a different product of that, or intermediate product of that reaction. Now, when I write the mechanism, I will be ignoring these other possibility steps. And the reason for that is that those steps will not lead us to our desired observed product. So those steps definitely do occur, but if we look at this diagram, what we can see is if we protonate on a different atom from the one that we intended, and then that does some other kind of thing, eventually that series of steps will reach a dead end where it doesn't create stable products and it doesn't create our desired product. So because the reaction is reversible, once it hits the dead end, it will start going backwards until it gets to the intermediate product where we first branched out, and we will have another opportunity to protonate on the desired, or the atom that will give us our product, and move in the direction of the product. Okay, so let's look at phase one. So it turns out that phase one involves adding a weak nucleophile. And it turns out to add a weak nucleophile, we are always going to do the same three steps. We're going to first protonate the carbonyl. As we discussed, we need to protonate the carbonyl to make it more reactive toward the weak nucleophile, and also to make the intermediate more stable so that it forms a protonated tetrahedral intermediate, which will not tend to go backwards very rapidly. We're then going to add the nucleophile. And then because weak nucleophiles generally are going to be neutral before they add, when they attach, they're going to gain positive formal charges. We're going to want to make those stable. And the easiest way to make them stable will be to remove a hydrogen plus. So we protonate, we add, and then we make stable, which we can abbreviate PAM, protonate, add, make stable. So here are the actual specific steps for acetal formation. We start with our carbonyl. We do a protonation reaction. Now, that's just an acid-base reaction. We've been writing those for a long time. I do want to point out that when we do a protonation, the pair of electrons from the carbonyl reaches out and grabs the hydrogen. So we make the arrow start on the lone pair, point toward the hydrogen, not the other direction. And then, of course, the hydrogen has to let go of the pair of electrons on the other side. So those go on to our conjugate base. We get an intermediate look like this. This is a protonated carbonyl. We have a positive charge On the carbonyl oxygen, we have a large partial positive on the carbonyl carbon. So now our weak nucleophile is attracted. One of its lone pairs comes over, makes a bond to the carbonyl carbon. To make room for that, we push one of the double bonds out onto the original oxygen. So we get a structure that looks like this. So this is an add step. Here's our product. At this point, if we look at our product, we can see that our alkoxy group has an extra hydrogen on it, has an extra bond to it, which makes it have a positive formal charge. We'd like to get rid of that formal charge. So base comes over, it removes the hydrogen, pair of electrons goes down onto the oxygen, so that now our alkoxy group has an oxygen with two bonds, two lone pairs, and it is neutral. Now, this is actually a very important intermediate called a hemiacetal. Down below, I'm going to show you how hemiacetals are very, very important part of carbohydrate chemistry that we see in biological carbohydrates like glucose. So a hemiacetal is going to be defined as a carbon that has an hydroxyl group, an OH, and an alkoxy OR group attached to the same carbon. You can see OH, OR. Okay, next step then is the remove OH, to remove the oxygen. So to do this, to remove something, the three steps are protonate, remove, make stable. So that would normally be abbreviated PRM. It turns out in this particular case, I'm going to show you that resonance allows us to skip the make stable step. So we are just going to protonate and remove PR. Okay, so we want to remove this hydroxyl group. The problem is that if it were to just leave, it becomes hydroxide, which is pretty strong base. It's not very stable. So in order to make it a better leaving group, what we're going to do is protonate it so that when it breaks off, it becomes a water, which is a much weaker base and much more stable. So we protonate on the hydroxyl lone pair right there. Again, it's grabbing the hydrogen. That's our P step. Now our hydroxyl group has become basically a water attached to the carbon. So that's going to leave. So we break the bond, it becomes a water and it leaves. And very often we abbreviate that in these mechanisms by putting the molecule that left in brackets and putting a minus sign over it, although that's not required. So I call this a removal step. We're removing that group from the molecule. Now, at this point, we've created this structure right here, where our carbonyl carbon now has only 3 groups attached. That's going to give it a positive formal charge. And normally, positive charges are going to be undesirable, and we would try to get rid of them by deprotonating. But in this particular case, we have another option. The adjacent OR alkoxy oxygen has lone pairs on it. So what we can do is we can use resonance, moving one of those lone pairs down to make a double bond and delocalizing that oxygen, that positive charge out onto the oxygen, so that in our intermediate, that positive charge is spread out and therefore doesn't have as much potential energy, and therefore it can exist like that for a period of time. We're now going to add our second alcohol. In order to do that, we would normally protonate the carbonyl oxygen to give it a positive formal charge. We would then add and make stable. In this case, we can skip the protonate step, because if we look at our intermediate, it essentially has a carbon in place of where the hydrogen would go if we were to protonate. So this intermediate is very much analogous to, I'm going to scroll back up, this intermediate right here, which was the intermediate we got in the first phase by protonating. So we're going to go straight to the addition step because it's already activated for addition. The oxygen of the alcohol It's going to take a lone pair, make a bond to the carbonyl carbon, push a pair of electrons out of the way, and again, we get an intermediate which has these two oxygens attached, but one of the groups has an extra hydrogen, has three bonds, only one lone pair, has a positive formal charge. So in order to make that stable, in our last step, we're going to take base, we're going to remove that proton right there, a pair of electrons will go down on the oxygen, and that's our final product. So our last phase is A and M, add and make stable. So therefore, we can memorize this overall mechanism by memorizing this acronym. Protonate, add, make stable. Protonate, remove, add, make stable. PAM-PRAM. Now let's talk briefly about hemiacetals. Hemiacetals are usually unstable, especially in base. The reason for this is that if we look at the hemiacetal where it has an OH and an OR, the OH is a weak acid. So in base can come over, remove the proton from the OH, a pair of electrons will go onto oxygen, and that's going to create a tetrahedral intermediate. And what we know about the tetrahedral intermediate is that it's very unstable. Electron pressure from the negatively charged oxygen is going to push down and push out the alkoxide, and therefore the hemiacetal is going to tend to decompose back to a ketone or aldehyde, and then alkoxide, which could be protonated or something at a later state. There is, however, a situation where hemiacetals become reasonably stable, and that is when they form rings. This is an extremely important part of sugar chemistry or carbohydrate chemistry that is observed in biological systems. For example, if we look at the canonical biological sugar glucose, D-glucose very readily forms a cyclic hemiacetal, and this is a really important part of its function in biological systems. Okay, so let's take a look at this. So this molecule here, this is D-glucose. Now, carbohydrates are characterized by having chain of carbons. This one is 6 carbons long. One carbon has a carbonyl, a double bond O, and all of the rest of the carbons have one OH, one hydroxyl group directly attached. Now, this is drawn in sort of the biochemist way of drawing it. So it's a biochemist form of a Fischer projection. Normally, we don't put carbon atoms at the carbon chains of a Fischer projection, but in biochemistry they do. But they are intending to show stereochemistry in the Fischer projection way. So this particular glucose molecule has the hydroxyl groups arranged in a particular direction to show their stereochemistry. And in order to remember the stereochemistry of glucose, I've sort of come up with a little mnemonic, because this is exactly the kind of thing that I have a hard time remembering if I don't do something to help myself. So starting on carbon 2, which is the first carbon that has a hydroxyl, the OHs go right, left, right, right. And then the OH on the end is not a stereo center, it's not a chirality center, so we can just write CH2OH in that case. So remember that D-glucose is always right, left, right, right. Okay, so cyclic hemiacetal. So what happens in the cyclic hemiacetal formation, this is not a mechanism, this is the overall observed reaction, is that the hydroxyl group from carbon 5, so the one second on the, on the carbon, one carbon from the end, not the direct end carbon, bends around and makes a bond to the C double bond O carbon of the aldehyde at carbon 1. Now, why this one? Well, the reason why this hydroxyl reacts is that if we count out the number of atoms that would be in the ring, starting here, because we're making a bond to that carbon, 1, 2, 3, for 5 carbons, this oxygen forms the 6th atom of the ring. If we were to go out to the very end, it would make a 7-membered ring, which we know is less stable, right? 6-membered rings have the least amount of ring strength. So this oxygen folds around. It's acting like carbon OH, right? Like ROH. It's just that it's part of a very complicated carbon group that's in the same molecule as the C double bond O. So the ROH comes over, it makes a bond here, pushes a pair of electrons out, gets protonated, so it makes an OH there. So now we have a ring starting here, coming around, coming back, ring of carbons, but the ring itself is now a hemiacetal ring because if we look at carbon 1, that carbon has oxygen, carbon, right? OR, oxygen, hydrogen, OH attached to the same carbon. So that is a hemiacetal carbon. We can redraw this, and in fact, it is often redrawn in more of a ring shape instead of this weird bendy long bond here making the connection, which looks like this. This is called a Haworth projection, and we will discuss these more when we do carbohydrates. We can see then that this would be 1, 2, 3, 4, 5. Then we go to the oxygen, that's 6, then back to carbon 1. Here's our hemiacetal. We have OR and we have OH. And then these up and downs represent the actual stereochemistry, which you don't need to worry about right now. I'm just doing it for accuracy. And then finally, this carbon becomes a new stereocenter, new chirality center, actually. And the OH can go either up or down. Because it's random, well, semi-random, we get a mixture of them. And to indicate a mixture of wedges and dashes, we actually use these squiggly bonds right here. Okay, now another feature that's very important of acetal chemistry is that acetals can be formed and then they can be converted back to the original ketone. This is generally done with aqueous acid, usually something like we could write H3O plus or H3O plus aqueous, or sometimes you'll see it written as H3O plus hydronium and water. But where do we get this? Well, dilute H2SO4, aqueous hydrochloric acid, these kinds of acids are what we would generally put in there. What we would observe then is the two alkoxy groups would break off and become protonated, so they'd become alcohols again, and then this oxygen actually would become the oxygen of the carbonyl. The mechanism of this is the exact same as the mechanism of the acetal formation, just in reverse. So in reverse direction, a protonate becomes a make stable step. An add step becomes a remove step. A remove step becomes an add step, and a make stable becomes a protonate. So what we get in this case then, if we look, we protonate, we remove, we get the resonance stabilized intermediate that we don't have to do anything to, then we add, then we make stable, then we protonate, remove. So the acronym in the reverse direction is PRAM-PERM. There's a couple of other interesting uses for acetals. If we use a diol, so that would be a molecule that has 2 OHs attached to the carbon chain, we can actually form a cyclic acetal. So here's an example. If we were to use this ketone, treat it with that molecule has a common name, ethylene glycol. It's basically 2 carbons, OH on each carbon. Ethylene glycol. You could also call it ethane diol, although almost nobody does. So ethylene glycol, PTSA, our strong acid. And what happens is this oxygen makes a bond here, then the other oxygen makes a bond there. The carbonyl oxygen is removed as water, and we get this molecule where here's the first oxygen attached, here's the second oxygen attached, and because they are both part of the same molecule, the rest of the molecule forms a ring. So here is our acetal carbon. We can recognize by having two OR groups attached. Now, why would we want to do this? Well, we want to do this because cyclic acetals are often used as protecting groups to prevent a carbonyl from reacting when we don't want it to react. So a protecting group is a group that we can put on in a chemical reaction. It will change the functional group into something that's unreactive, but then later on we can remove it and regenerate the original functional group. Let me show you an example of how this might be used. So let's say, for example, that we had this molecule right here. 5-membered ring, aldehyde branching off, ketone in the ring. And that what we wanted to do was convert the ketone carbonyl into an alcohol. Now, the problem with this is that, as we mentioned, aldehydes are more reactive. So if we were to, for example, use sodium borohydride, which we're going to review again later, but sodium borohydride adds hydrogen minus and converts C double bond O's into OHs. If we were to carefully add one equivalent so that only one of these would potentially react, unfortunately, the one that would react would be the aldehyde. We would get this molecule. This is the exact opposite of what we want. The aldehyde is OH, the ketone is still a ketone. So what do? Well, what we can do is take advantage of the fact that the aldehyde is more reactive by carefully adding one equivalent of ethylene glycol and acid. We can selectively convert the aldehyde into an acetal. Now, acetals do not react with sodium borohydride. So therefore, we can put as much sodium borohydride as we want to completely convert the ketone into a hydroxyl group. And then after that reaction is done, all we have to do is add hydronium, and the acetal will convert back into the aldehyde, and now we have our desired product.